Hey guys, welcome to section 1.2, which I'm calling all about functions. Of course, I think I've called everything so far in this chapter all about functions, but specifically we're going to be dealing with these topics: increasing, decreasing, and constant functions, minima and maxima, and even and odd functions. Plus, as we go along, we'll have a review of piece functions and a review of finding the domain and range. So basically, I guess you can figure out that whatever we do, we keep revisiting those topics again and again and again. So let's start now by talking about increasing functions, decreasing functions, and constant functions. I've got a sheet of paper here that has three different types of functions, but what I'm going to do is I'm going to cover up all but one of them just because I want to try to focus on just this first parabola. So everybody look at this parabola, and the key thing to evaluating whether a function is increasing, decreasing, or constant is no matter how you look at it, or which way the arrows go, you always have to evaluate this function from left to right. And this is absolutely essential. So what I'm going to do is I'm going to take this parabola and I'm going to look at this parabola as it is going from left to right. And you see I'm tracing it with this red pen, and you see what's happening? It's going down. From here to here, it's going down. So I'm going to put a D right there. That function is decreasing right there. And then it gets to this origin right here, which is the vertex of this particular function. And then it switches directions and it becomes an increasing function. Now, constant would mean it's not changing, so we don't even have a constant in this one. So if I were to ask you to discuss where this function is increasing and decreasing, you would say that it is decreasing from negative infinity to 0. And we're going to leave a soft bracket there because 0 is the beginning of the increase and the end of the decrease. So we'll just use a soft bracket. And then it is increasing from 0 to positive infinity. Now notice we answer in terms of the x-axis. In other words, that's the decrease, and then this is the increase as we move from left to right. Now again, I see that arrow going up right there. I see it going up, and the tendency is to say, oh, it's increasing right there because it's going up. But remember, this is key. You have to read from left to right, always from left to right. Okay, let's look at the second function. I'm going to uncover it now. There it is. This is a cubic function, and I want to know whether it is increasing, decreasing, or constant. So we find the leftmost part of the function, which is over here, and we start moving our pen, and you can see we're going up, 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 and we keep going up. So this function is always increasing. And I know you say, well, what if I'm left-handed? What if I want to read it the other way? If you read it like this, wouldn't it be always decreasing? Well, yes, but you don't have that option. The definition of increasing or decreasing or constant functions is always determined as we move from left to right. So as we go left to right on this function, it is always increasing. So therefore, it is increasing over its entire domain, which is from negative to positive infinity, and it's never decreasing and it's never constant. Third example. I had to get one in here that had a little constancy, so let me show you this. Push this up just a little bit. Okay, so where is this function increasing? Where is this function decreasing? And where is this function constant? All right, so let's start over on the left-hand side. And I don't care about the arrow pointing up. That doesn't matter. As we move down, this function is decreasing. Okay? And then we get to here, and we turn around, and this function is increasing. So I'll put a little I there. And then you see this part right here that's just flat? This is an example of constancy. It's not growing. It's not moving up and down. It's flat. It's flatlining. And then it switches and it increases again. So let's go with my pen. It goes down, then it goes up, then it stays flat. So this is constant, and then it goes up again. All right, now let's see if we can write increasing, decreasing, and constant areas. It is decreasing from just this part, and that is from negative infinity up to negative 3. We're always answering in terms of the domain. Then it is constant. Let's go ahead and do this part. It is constant between 0 and 5. 0 to 5. And that means it is increasing from this point right here, from negative 3 up to 0, and also from 5 to positive infinity. Now again, always answer. I'm going to write this little note for you. Always answer in terms of the domain. Look at the X. You're looking at the picture of the graph, but you want to answer your increasing, decreasing, and constant in terms of the domain, which is the X term. So we're going from this X to this X, which is negative infinity to negative 3. That's your decrease. Then we're increasing from negative 3 to 0. Then we're constant from 0 to 5. Then we're increasing again from 5 to positive infinity. So we always answer in terms of the domain. Increasing, decreasing, and constant functions. Okay, the second part of our discussion today is about minimum and maximum points. And we're going to talk about two types of minimum and maximums. Okay, I have drawn two graphs here. The first one is the graph of an absolute value graph. It's a V. And I want you to look at this point right here. That is the origin, 0, 0. Now that point, you would say, is definitely the lowest piece, lowest point on this graph. As we move this way from the origin, it's going up, 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 up. As we go this way, it's going up, 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 up. That is definitely the lowest point on the graph. We call that a minimum. And the singular of that is minimum. And if you have more than one, you call it minima. It's a Latin ending. Because this is the absolute lowest point on this graph, we call this an absolute minimum. Okay? Now look right below it. This is a parabola. And you can see that this point, which is the vertex, is the highest point on that graph, and it is never going to go higher than that. So this would be called an absolute maximum point. Now these both are pretty simple. They have an absolute minimum or an absolute maximum point, but it's not always so clear. Look at this particular graph that I'm just going to sketch up here. So it goes like this, and then it bumps and turns, and it goes like this. Now, is that a function? Well, it's supposed to be. Actually, I need to draw it. I got it looking a little bit. Let's draw it like that. Okay, now that's better. Okay, now it is supposed to be a function. Look at the vertical line test. All right, now what's going on right here is you know what, that is still a terrible picture. Let me try this one more time. I'm going to get this a little better for you. Okay, so let's do this. Comes like that, then let's make it do this. Okay, so I can really show you what I was going to show you. All right, now, you see this point right here? It's pretty low, but it is not the lowest point on this graph. It is the lowest point in this particular area. So we call that a relative minimum. In this particular part of the graph, it's low. It's the lowest part. It's the lowest point for a while. In fact, it's the lowest point on the graph until you start this downward spiral that goes to infinity. See this point right here? This is the highest point on that area of the graph. So we call this a relative maximum. And these points can tell you something about a graph. Maximum, mum. But there is no absolute maximum or min because this graph goes to infinity. You see, the minimum just keeps getting lower and lower, and here the maximum keeps getting lower and lower. So when you talk about maximum and minimum points, you're going to talk about relative and absolute, and it just depends. Let's go back to my example just a minute ago. These two graphs, which are common, an absolute value graph here and a parabola, these both have absolute max and mins. But this graph right here, which kind of snakes around, doesn't have absolutes. However, these points could be referred to as your relative maximum and minimum points. Okay, last thing on this set of instructions will be even functions and odd functions. Okay, even functions and odd functions are determined by two things. I like to do it with symmetry. I'm going to put even on this side and odd on this side. But you're going to also see something that has to do with their exponents. All right, now let's take the parabola y is equal to x squared. Okay, it looks like this. It has a vertex at the origin, and it goes up, and it goes up. Now, you will notice that this function has y-axis symmetry, which means if I folded this graph across the y-axis, this left side would fall on top of the right side. This function is even. Now there's another way to figure out if a function is even, and that is if you put in a number like f of 1, and then you put in the inverse, and they equal the same thing, then you have even symmetry. So if I put 1 into this function, I would get out a 1. And if I put negative 1 into this function, I would get out the same thing. See this? It would work if I did 2 and negative 2 or 3 and negative 3. So when that happens, when you get the same value, when you put in a positive and negative number, you have an even function. So two things, even function have the same value, and also they have y-axis symmetry. Now here's an example of an odd function. An odd function, here is cube again. This is y equals x cubed. All right, two things to look for. If you put in a positive number like 2, you will get 2 cubed, which is 8. If you put in the negative value, you will get negative 2 cubed, which is negative 8. You see how these are opposites? Okay, when that happens, when they're not the same, but they have opposite signs, this is an odd function. And its symmetry is described as origin symmetry. And origin symmetry just means that both signs of the points are reversed. For example, here's a point on this graph, 2, 8. That point appears on the other side of the graph with both of its signs changed. So for every point up here, there is an equal point down here, a matching point with the opposite signs. That's origin symmetry. So these are even and odd functions. Now, some functions are neither. Here's an example of a function that is neither. If you take the function y equals x squared plus 3x plus 2, and I ask you if that's even or odd. Well, let's evaluate the function at 1, and you're going to get 1 squared plus 3 plus 2, which is 6. If you evaluate at negative 1, you're going to get negative 1 squared plus 3 times negative 1 plus 2. That's 1 minus 3 plus 2, which is 0. See these two answers? They're not opposites. They're not the same. So this function is neither even nor odd. That's all for tonight. Got to quickly end. I got 8 seconds left. Thanks for listening. See you tomorrow.